Okay, this is 12.3, video 2. Now that we've kind of talked about how to find the dot product and now the meaning of it and some of the applications, let's go ahead and put those into practice. So we're going to find in letter number 3 here, we're going to find the angle between two vectors. So we're given vector 215 and vector 420. Let's find the angle in between them. Well, we have a formula for that, which is A dot B equals magnitude A, magnitude B, cosine of the angle in between. So if I want to find these, I'm going to find the dot product. I'm going to find the magnitudes of A and B, and then we'll solve for theta. So let's see, the dot product is going to be 2 times 4 is 8, 1 times 2 is 2, and 5 times 0 is 0. The magnitude of A is going to be the square root of each component squared added together, so that's 4 plus 1 plus 25. The magnitude of B, excuse me, is the square root of 16 plus 4 plus 0, and then cosine of theta. So we're going to get that 10 equals, what is that, square root of 30 times the square root of 20, it looks like, cosine of theta. So we get that cosine of theta is equal to 10 divided by the two square roots multiplied together. You can multiply what's underneath the square roots, and we would get the square root of 600. That actually simplifies, but in this case it's not really necessary, because what we want here is we actually want the angle, and unlike in calculus ABBC, we're going to go ahead and put this in degrees. So make sure your calculator is in degree mode. So theta is going to equal the inverse cosine of 10 over root 600, which is going to be approximately, you plug that in, 65.91 degrees. And yes, we will be primarily using degrees when we have to do angles in this course. So there you go. Angle in between is approximately 65.91 degrees in between those two vectors. Okay, number 4. Let vector A be 216, vector B is 13C. So we want to find C such that vector A and vector B are perpendicular. Well, we do know that if two vectors are perpendicular, then their dot product has to equal 0. So I know that vector, I know that vector A dot vector B is 0. So if we dot A and B, so we're going to get 2 times 1, which is 2, 1 times 3, which is 3, and 6 times C, which is 6C. That product has, that dot product has to equal 0. So I've got that 5 plus 6C equals 0. Subtracting 5, we get 6C equals negative 5, or C is negative 5/6. There's the value of C, because we knew that for two vectors to be perpendicular, the dot product was 0. All right, moving on. Now we're going to talk about this thing which is called a direction angle. And a direction angle simply is the angle that is made with the coordinate axis. So if you have some kind of a vector, it's going to make a specific angle with each one of the axes, the x, the y, and the z axes. We call the direction angle that was made with the x-axis alpha. We call the one with the y-axis beta, and the z-axis we call it gamma. So we're going to be given the vector 2, 6, 3. We want to find the direction angle. So just illustrating this, so we have somewhat of an idea what we're looking at here. So there's z, there's x. There's y. Let's see, we want to do the vector 2, 6, 3. So vector 2, 6, 3 is going to go out 2 units in the x direction, 6 units in the y direction. 1, 2, 3, 4, 5, 6. And then 3 units up in the z direction. So if we trace this by using dots, let's see, kind of dotting it out there, staying parallel to the y-axis as best as I can. Not the best job there. And then up 3 units. 1, 2, 3. Somewhere around here is going to be the tip coming from the origin. It's going to look something like that. All right. So now, like I said, you have a direction angle, which is an angle which is made with the axis. So in our case here, let's see, I'll use blue. This thing is going to make an angle from its projection down here. So it's going to make an angle from this way with the x-axis, and that's going to be your alpha. Okay, it's going to make an angle with the y-axis, which is actually going to go, it's going to be really hard to do here. I'll kind of try and draw it here from here to here. So from the orange down to the y-axis, that one right there is going to be your beta. And then it's going to make an angle with the z-axis, which is going to go like this, and that one's going to be your gamma. Those are the direction angles that we're looking at. All right, so what we need to do is we need to figure out what the direction angles are. So if you're going to make a direction angle with the x-axis, you want to find the angle in between the vector that we're given and a vector which represents the x-axis. Well, the easiest one to use is the unit vector in the direction of the x-axis, which is I, or 1, 0, 0. So if we want to use 1, 0, 0, we're going to dot that with our vector 2, 6, 3, because again 1, 0, 0 is a vector on the x-axis. So we're going to find the angle in between. So then we need to find the magnitudes of each one of these vectors. Well, the nice thing about the unit vector is the magnitude is 1. Oops, don't need the absolute value. The magnitude is 1. Now I need the square root of 4 plus 36 plus 9 cosine of alpha. So let's see, on the left side we're going to do the dot product. We're going to get 2 plus 0 plus 0. That's nice, so it's just 2. On the right side we're going to get 1 times the square root of, let's see, 4 and 36 is 40 plus 9 is 49. So that's nice. Square root of 49 is 7. So we get 1 times 7, or 7, cosine of alpha. So that means solving this thing, we're going to get 2/7 equals the cosine of alpha. To solve for alpha, it's going to be the inverse cosine of 2/7. Let's make that an actual 7. Okay, and then you're going to actually follow a very similar process to find beta and to find gamma. Beta is going to end up being the inverse cosine, inverse cosine of 6/7. And you might think, well, how did I get that so fast? Well, think about it. The 7 is coming from the magnitude of the given vector. That's going to be the same no matter what. So you're always going to have 7 times that. I don't have to worry about which this particular piece right here, because that's always going to be 1 as long as you use the unit vector in the direction of x, y, or z. So the left side is going to make a difference, because if I use y, it's going to be 0, 1, 0. So when I dot that, the only thing that gets multiplied times a non-zero is the middle one, which is 6. So that's why I'm getting the y component over the magnitude of the given vector. So if you can piece that together, or everything that I just said there, then you can figure out that gamma is going to be the inverse cosine, in this case, of the z component, which is 3, over the magnitude of the given vector, 3/7. I'm not worried about figuring out what the actual decimal approximations are. That's how you would find direction angles. Biggest thing there is a direction angle, once again, is an angle which is made with the specific axes. That's what you're doing there. So let's kind of put that into a basic formula that just says that alpha is going to be the inverse cosine of A1 over magnitude A. Beta is inverse cosine of A2 over magnitude A. And gamma is inverse cosine of A3 over magnitude A. All right, and that'll always be the case. All right, for this next one, this is one where I really wish that I had you guys in class to actually see this, but a projection, while you can just memorize a formula, I'm hoping that we can actually make some sense of this. What I would tell you to do is, if you can, take 2 pencils of equal length and hold them so that you connect like the erasers or something like that, so it's like 2 vectors in space, and hold them at such an angle such that they're not at a right angle to each other, just some other angle in between. And then look straight down, or hold one of them flat on the table and then look straight down on it. What should look like is the pencil that is the one that's raised in the air should look like, if you look straight down on it, it's shorter than the other one, even though you know that they're the same length. So let me kind of illustrate that. It's much easier to see when we're actually in a classroom. So let's say that I have this particular vector right here, and then this particular vector, let's go in blue, right here. Okay, those vectors may actually be the exact same length. The idea is, if I was looking and I placed the black vector down on the table and I look straight down on the blue vector, it's going to make a projection down onto this black vector right here. So if I kind of shine a light down from the top, it'll actually project the shadow of that blue vector, and it would actually come down and hit this the black vector right where you see the red line stop. So there's an angle in between, whatever that angle is. We'll call it theta. There's 2 pieces that we're going to get out of this. There is what's called a component of B in the direction of A. So there's what's called a component of B, and let me label these properly. That's vector B, and vector A is the black one, which is the entire vector A. There is what's called a component of B onto or in the direction of vector A. Well, that is going to look like this orange one. This piece right here is the component of vector B onto vector A, and that's the way it's written. Component of B onto A, and I always remember the onto part because B looks like it's kind of sitting on top of A when you write it like that. And how did we get that? Well, we projected B down onto A. So this part right here gives you the component of B, which is perpendicular to A. That's the red part. So a note here is there will always, whoops, wrong one. There will always be a component of B in the direction of A. So when you have two vectors, you're always going to have some kind of a component that you could project down there, and it'll always be a component of B in the direction of A. And that, again, is this part right here, that length right there. And what I'm going to tell you is the component is a scalar. Okay, the component is going to work out to be a scalar. It's just basically telling you what's the length of that particular vector that's projected down onto A. The vector itself will actually be the projection, and that will be a vector as opposed to a scalar. So let's see how we come up with these things. So the first thing is, you can see that we formed a right triangle. What I know is that the cosine of theta is the adjacent side over the hypotenuse. Well, the adjacent side, because remember these are lengths now, the adjacent side is that component of B onto A, and the hypotenuse is the magnitude of vector B. Okay, it's the actual length of vector B. If I were to solve this, if I were to solve this part equaling this part right here, if I was to solve these two things for the component, all I have to do is multiply both sides by the magnitude of B. So what I'm going to get is magnitude of B cosine of theta equals the component of B onto A. All right, well, this part, maybe you're not going to follow as well, or maybe you will. I can multiply both sides by the magnitude of A. And hopefully you're going to see why I would do that. Multiplying both sides by the magnitude of A. If you're thinking back to what we've already done, the magnitude of A, magnitude of B, cosine of theta is the same thing as the dot product of A and B. So what this gave us was the dot product, A dotted with B. So I get magnitude A, component of B onto A. So now if I want to find the component of B onto A, all in terms of vectors, I can just divide by the magnitude of A. And we're going to get the component of B onto A is A dot B over magnitude of A. That's how you're going to find the component of B. And again, that should be a scalar. If you take two vectors and dot them on top, you get a scalar. Divided by a magnitude, which is also a scalar, you get a scalar. So again, this component of B onto A is literally just the length of that orange vector up there in the in the drawing. All right, so now let's figure out how this is going to get us to a projection. So again, this is the length of the projected vector. That's what we just found. So that vector that we just found is going to be parallel to A. So this vector will be parallel to vector A. So if I were to take vector A and I were to divide it by its magnitude, we get a unit vector. Which is in the direction of A. And then if we want to find the actual vector of orange, we'll take that unit vector and we'll multiply it by the desired length. Well, that desired length we just found, which was the component. So if I want to find the projection, write this in green, the projection of B onto A, now we're actually going to find that orange vector. Go ahead and write this next part in orange, I guess, since that's what it was. It's going to be a unit vector in the direction of A times the component. So the component was A dot B over magnitude A. And then we take that and multiply it by the unit vector, which is which is A divided by magnitude A. And of course that can be shortened just a little bit, because if I multiply those denominators together, the magnitude of A times the magnitude of A is just the magnitude of A squared. And on top we still have A dot B, which is going to give us, make those arrows look a little bit better, which is going to give us a scalar, and then we're going to multiply that by the original vector. Oops. We're going to multiply that by A. So again, what you want to think, and this is probably the easiest way to think about it, this piece right here, that's your component. That's all that is. That's the length of the projected vector. This piece right here is a unit vector in the direction of A. So if I take a unit vector and multiply it by a desired length, then I'm going to get the vector of the projection. So that's going to tell me what this orange projection vector was above. Okay, hopefully that makes sense. If it doesn't, the easiest thing to do is just to memorize these formulas. Best thing I can tell you. All right. So let's actually find a projection of B onto A. We are given vectors A and B, and now in this case these are two-dimensional. So let's find the projection of B onto A. Well, that's the dot product of A and B divided by the magnitude of A times vector A over the magnitude of A. Again, component times a unit vector. Length times the unit vector gives us the vector in the correct direction. That's the projection. So let's just do this. Dot product is going to be 3 times 2, which is 6, plus 1 times 7, which is 7. The magnitude of A is going to be the square root of 9 plus 1, so it's root 10, times vector A, which is 3, 1, over root 10. So let's see, I can multiply the two roots together and get 10. On top I get 13, so we get 13 tenths times the vector 3, 1. And you can distribute that, or you can leave it just as it is. Don't really have to do it in any specific form. Perfectly fine the way it is. And I think that works out to be, I don't know, doesn't even matter. Going to try and approximate a decimal, but that doesn't matter. Okay, a couple more things to talk about. Work. Okay, in the general sense, let's see if I can illustrate this one. So work. The idea is, if you are here, again, I apologize for my crude drawings, and you have a box sitting on the floor. So let's sketch a floor in here. And obviously we have to say here that friction is negligible here, because otherwise that adds a whole different component to it. But if you want to push this box in that direction, okay, and you're pushing from the top of the box, if you push straight at the top of the box, in other words, if you push in that direction at the top of the box, more than likely you're going to actually flip the box over. You're not actually going to get the proper amount of push to it. But what you're actually going to be doing, more than likely, is you're going to be pushing at some kind of an angle on the box. So you're actually going to be pushing in that direction to get this thing to slide across the floor. Well, what that does is it creates a force in that direction, a force which is actually going somewhat into the floor. This force right here is a vector. Force is a vector. I've got an angle in between the floor and the force. Well, the work done is actually going to be the amount of work that is done in that direction, because that's what we're trying to do. We're trying to get this thing to slide across the floor. But you also have another component of your force, which is in this direction. But there is no work done in that direction because of the fact that the box is actually not going down. Okay, it cannot actually go in the down direction because the floor is preventing it from going that way. So the work done is going to all be done in this direction. So it's going to be done in a, I guess you would say, parallel to the floor. But what that is that's the adjacent side where the force is the hypotenuse. So the work done is going to be based upon the fact that the cosine of the angle is equal to the, again, adjacent over hypotenuse. So the work done over the magnitude of the force. Let me go ahead and rewrite that. Magnitude of the force. And that is a vector, so I should be putting that vector symbol on top of there. So if I want to solve for work, it's just going to be magnitude of the force, cosine of the angle in between, is the work done. Okay, and you might remember from some of your sciences that force is the same thing as mass times distance, or I'm sorry, mass times acceleration. Excuse me, force is mass times acceleration. But ultimately, what that gives us is this: the work done is going to be the magnitude of the distance times the magnitude of the force times the cosine of theta. And that's because the magnitude of the distance is the top part, the magnitude of the force is the bottom, or the hypotenuse, and then cosine of theta is the angle in between those. So really what you get, because if you remember, magnitude of one vector times magnitude of another vector times cosine of theta is just the dot product. The work done is the same thing as D, that should be a D, not a P, is D dot F. A relatively simple formula. So work done is magnitude D, magnitude F dotted together. That's it. All right, last page. This should be relatively short, I hope. The video is getting long, apologize. So find the work done by pulling a sled 25 meters if the handle makes an angle of 38 degrees with the ground and a constant force of 12 newtons is applied. So relatively simple. We've got our force vector here. We've got a distance here. So the magnitude of the force they gave us is 12 newtons. That's how much force is applied. The distance, in this case, and you can put the absolute values, but it's just a distance, is 25 meters. So if we're going to multiply those things together, because in this case, they're both already just distances, they're already magnitudes, you're going to get the 12 newtons times 25 meters, oops, not equals, times the cosine of 38 degrees is, and you have to plug this into your calculator, and I believe you end up with 236.4 Newton meters, which is the same thing as a joule. Okay, forgot to put my 38 degrees in between there. All right, one more. Find the work done from moving a particle from 025 to 317, notice those are points, not vectors, by using a force vector of 2, 6, negative 7. So once again, work is force times distance, or force dot d. So work is, well, let's see, we have a force vector, which is 2, 6, negative 7. What we don't yet have is a distance vector. Well, we can find a distance vector simply by creating a vector between the 2 points, which is really just subtracting the ending point minus the beginning point. So the vector is going to be created as 3, negative 1, 2. And again, I hope that makes sense. 3 minus 0, 1 minus 2, 7 minus 5. And then the work is going to end up being the dot product, which is 6 minus 6 minus 14. So we're going to get minus 14 joules. All right, plenty long enough for this video. I apologize for the length of the video, but there you have it.